Think about the last time you looked up at the night sky and felt that deep, humbling pull of wonder. The stars seem endless, stretching beyond what our eyes can see. But what if I told you everything we observe is just the tiniest fraction of existence? Beyond the familiar glow of galaxies and nebulae lies the edge of the universe, a frontier so vast and strange it defies even our wildest imaginations. This is where the known rules of physics start to unravel, where light bends in impossible ways, and where mysteries pile upon mysteries like layers of an infinite cosmic onion. We've sent probes to distant planets, peered back in time to the birth of the first stars, and yet the universe keeps its most shocking secrets tucked away at its very edges. What lurks out there? Is space truly infinite, or does it have a boundary, a wall beyond which nothing exists? Could entire other universes be brushing against ours, invisible and undetectable? These aren't just questions for philosophers or scientists. They're puzzles that tug at the very fabric of reality, and today we're diving headfirst into 30 of the most jaw-dropping enigmas hiding in the darkness. From ghostly echoes of the Big Bang to bizarre regions where time itself might flow backward, each mystery we'll uncover is more mind-bending than the last. Some might keep astronomers awake at night, others could rewrite everything we thought we knew about existence. So buckle up, because we're not just exploring space. We're venturing to the ragged edge of the comprehensible, where the universe stops playing by the rules and starts revealing how little we truly understand. Ready to have your reality stretched? Let's begin. The first jaw-dropping mystery starts right here, with everything we can possibly see. Imagine the universe as an enormous cosmic spotlight, shining only so far into the darkness. That's essentially what astronomers call the observable universe, the portion of existence where light has had enough time, over 13.8 billion years, to finally reach our telescopes. But here's the catch: no matter how powerful our instruments get, there's a hard boundary we can never peek beyond. Why? Picture throwing a stone into a still pond. The ripples spread outward, but they take time to travel. Now replace that stone with the Big Bang and those ripples with light. The farther away a galaxy is, the longer its light has been journeying toward us. But the universe hasn't existed forever. It had a beginning. That means light from the most distant regions simply hasn't had enough time to arrive beyond that. Pure cosmic guesswork. We're staring at a horizon just like a sailor spotting the curve of the Earth, knowing there's more ocean but unable to see past it. And it gets weirder, because the universe is expanding, and not just expanding, it's accelerating. Galaxies at the very edge are being pulled away from us faster than light can bridge the gap. That means their light will never reach Earth, no matter how long we wait. They've crossed a point of no return, vanishing forever behind what scientists call the cosmic event horizon. It's not just a barrier of distance, it's a barrier of physics, locking away whatever lies beyond like a vault we can't crack. So what's out there? More of the same, just endlessly repeating. Or something so bizarre our brains couldn't process it. The unsettling truth is, we'll likely never know. The observable universe might be all we ever get to study, a glowing island in an ocean of permanent mystery. But that's what makes it so thrilling. Every time we point a telescope skyward, we're not just looking at stars. We're staring at the edge of the knowable, where science meets the ultimate question mark. Now let's zoom in on one of the most baffling gravitational puzzles in our cosmic neighborhood, something so massive. It's yanking entire galaxies toward it like a hidden cosmic magnet. Scientists call it the Great Attractor, a mysterious region of space roughly 250 million light-years away that's pulling the Milky Way, Andromeda, and hundreds of other galaxies toward it at over 14 million miles per hour. But here's the catch: we can't actually see what's doing the pulling. At first, astronomers thought it might be a colossal cluster of galaxies, a giant knot of matter with enough gravity to drag everything nearby into its grip. But when they pointed telescopes in that direction, they hit a roadblock. Our own galaxy's dusty disk blocks the view, like trying to peer through a fogged-up windshield. What little we can see suggests there's not nearly enough visible matter there to explain the insane gravitational tug. So what's the culprit? One leading theory points to dark matter, that invisible, mysterious stuff that makes up most of the universe's mass. Could there be a sprawling web of dark matter, dense and massive enough to warp the motion of galaxies on this scale? But the plot thickens. Recent observations hint that the Great Attractor might just be the tip of something even bigger, a mind-boggling supercluster called Laniakea, Hawaiian for immeasurable heaven. This cosmic metropolis spans 500 million light-years, with thousands of galaxies drifting like leaves caught in a river's current, all flowing toward the same unseen destination. It's as if the universe has built an invisible highway system, and everything in our corner of space is being funneled down the same gravitational on-ramp. The strangest part, we still don't know what's at the end of that highway. Some speculate it could be an unimaginably vast concentration of matter, a cosmic anomaly that defies our current physics. Others wonder if the Great Attractor is just one thread in a larger tapestry, part of a pattern we're only beginning to decipher. One thing's certain, every galaxy caught in this flow is on a one-way trip toward something we can't yet comprehend. A reminder that even the structures we think of as local are still hiding secrets big enough to rewrite the rules. If the Great Attractor is a cosmic vacuum pulling everything toward it, then the void of Boötes is its opposite, a staggering abyss of nothingness so vast it shouldn't exist. Picture cutting a hole in the universe 700 million light-years wide, a bubble so empty that if you stood in its center, you wouldn't see a single galaxy with the naked eye. Astronomers call these places supervoids, but the void of Boötes isn't just any empty space. It's a cosmic anomaly that defies everything we know about how the universe arranges itself. Think of the universe like a sponge, galaxies clustered along filaments with smaller gaps between them. But the void of Boötes isn't a gap, it's a cavern. Discovered in the 1980s, this region holds only a handful of galaxies where there should be thousands. It's not just empty, it's aggressively empty, as if something scrubbed the area clean of matter. The few galaxies that do linger there seem strangely isolated, like lone survivors in a wasteland. Here's where it gets weird. According to our best models, the Big Bang's afterglow, the cosmic microwave background, should look slightly warmer in areas with supervoids, since photons traveling through them lose less energy fighting gravity. But when researchers studied the void of Boötes, they found the opposite, a bizarre cold spot, as if the void somehow sucked energy out of the light passing through it. Some theories suggest this could be evidence of a collision with another universe, a defect in space-time, or even a glitch in the very fabric of reality. The real puzzle, how did it form? The standard model of cosmic structure says voids this size shouldn't exist. Gravity should have pulled matter into at least some clusters over billions of years. One wild hypothesis proposes that dark energy, the mysterious force accelerating the universe's expansion, might work differently here, pushing matter away faster than gravity can gather it. Others wonder if we're seeing the fingerprints of quantum fluctuations from the universe's first moments, stretched to impossible scales. Whatever the explanation, the void of Boötes forces us to question whether we truly understand the rules of cosmic architecture. It's a blackboard erased clean, a silent challenge to our theories, and a reminder that the universe doesn't owe us tidy answers. Staring at the stars, you'd think measuring how fast the universe is growing would be straightforward. After all, we've had telescopes for centuries. But when the most advanced instruments humanity's ever built give us conflicting answers, that's when things get interesting. Welcome to the Hubble tension, a cosmic tug-of-war between two ways of measuring expansion that should agree but stubbornly refuse to. First, let's set the stage. In the 1920s, Edwin Hubble discovered galaxies were racing away from us, proving the universe wasn't static but stretching like warm taffy. Today, we calculate this expansion rate, the Hubble constant, using two main methods. One approach studies the cosmic microwave background, that ancient afterglow from the Big Bang. By mapping its tiny fluctuations with spacecraft like Planck, scientists extrapolate how fast space should be stretching now. The other method relies on standard candles, celestial objects like Cepheid variable stars and Type Ia supernova, whose predictable brightness lets us gauge distances to nearby galaxies. Here's the kicker: these methods keep giving different numbers. The cosmic microwave background suggests an expansion rate around 67 kilometers per second per megaparsec, meaning for every 3 million light years you go out, space stretches 67 kilometers faster every second. But when astronomers measure nearby stars and supernova, the rate jumps to roughly 73. That gap might sound small, but in cosmology, it's a screaming alarm bell. Why the mismatch? Either we're making measurement errors unlikely, given how often teams have double-checked, or the universe is playing by rules we haven't discovered yet. Some theorists speculate dark energy, the mysterious force accelerating expansion, might be changing strength over time. Others wonder if exotic particles like dark radiation flooded the early cosmos, tweaking its evolution. There's even a wild card idea. What if our pocket of the universe sits in a weird low-density bubble, making local measurements unrepresentative of the whole? The most thrilling possibility: this tension could crack open entirely new physics. Just like the orbit of Mercury revealed gaps in Newton's gravity that only Einstein could explain, the Hubble tension might be pointing to something beyond our current models, a cosmic clue waiting to rewrite the textbooks. Until then, every telescope trained on the night sky is hunting for answers, because in this numbers game, the universe is clearly hiding something big. What if I told you entire clusters of galaxies are being swept across the cosmos like leaves in a river, toward something we can't see, can't map, and might never understand? That's the eerie reality of dark flow, one of the most unsettling mysteries at the edge of our understanding. Back in 2008, astronomers studying the motion of over 1,000 galaxy clusters noticed something that shouldn't happen. These colossal structures, each containing thousands of galaxies, were all moving in the same direction at breakneck speeds, up to 600 miles per second, as if pulled by an invisible hand. This wasn't just random drift. The clusters were racing toward a specific patch of sky between the constellations Centaurus and Vela, far beyond anything the Great Attractor could explain. The kicker: there's no known concentration of matter in that direction powerful enough to tug them. Not even dark matter, our usual cosmic scapegoat, can account for this motion. It's as if something outside our observable universe is exerting gravity on everything inside it, a cosmic puppeteer we'll never see. Now, let's unpack how bizarre this really is. According to standard cosmology, the universe should be expanding uniformly after the Big Bang, with matter distributed evenly enough that no single direction should dominate. Yet here we are, watching galaxies march in lockstep like soldiers to some unseen drum. One theory suggests these clusters are feeling the gravitational pull of a supermassive structure lurking beyond our cosmic horizon, perhaps a neighboring universe brushing against ours in the multiverse. Others propose space-time itself might be warped on scales we can't measure, funneling everything toward a gravitational slope we can't map, but skepticism lingers. Some researchers argue dark flow could be an illusion caused by incomplete data or measurement errors, though subsequent studies keep confirming the anomaly. The most mind-bending possibility: this flow might be evidence of a pre-Big Bang reality, a relic of whatever existed before our universe began, its gravity still echoing through the fabric of everything we know. Whatever the truth, dark flow forces us to confront an unsettling idea. The forces shaping our cosmos might not all live inside it. The edge of the universe isn't just a boundary, it could be a window, and whatever's on the other side is reaching in. If the universe is supposed to be random and isotropic, the same in all directions, then why does it seem to have a preferred axis? That's the unsettling question behind what scientists half-jokingly call the axis of evil, a pattern in the cosmic microwave background so bizarre it threatens to upend our understanding of the cosmos. When NASA WMAP satellite mapped the afterglow of the Big Bang in exquisite detail, researchers expected to see a soup of tiny temperature fluctuations, random seeds that would eventually grow into galaxies. Instead, they found something that sent chills down spines. The fluctuations weren't perfectly scrambled. They lined up along an eerie corridor stretching across the sky, like a ghostly highway pointing toward the constellations Leo and Virgo. Even stranger, the universe's large-scale structures, superclusters, voids, and filaments seem to subtly align with this axis too, as if space itself had a hidden spine. This wasn't just a fluke. Later missions like Planck confirmed the anomaly, though with less dramatic significance. The odds of this happening by chance? Less than 1 in 1,000. So what's causing it? One camp argues it's a systematic error, maybe dust in our galaxy contaminating the data, or an artifact of how we process the signals. But after years of scrutiny, no one's found a convincing glitch to explain it away. That leaves the far wilder possibilities. Could the axis be evidence of a pre-Big Bang structure, some imprint from an earlier universe that bled into ours? Or does it hint that dark energy isn't uniform, but Chinese letter, pulling space unevenly like an invisible tide? The most radical idea, that we're seeing the gravitational fingerprint of a neighboring universe brushing against ours in the multiverse, warping the fabric of reality on scales we can barely comprehend. The name Axis of Evil isn't just melodrama. It reflects how deeply this anomaly unsettles cosmologists. If real, it means the universe isn't just lopsided. It might have a primordial orientation, a preferred direction baked into existence itself. That would shatter one of cosmology's sacred principles, the Copernican idea that we don't occupy a special place in the cosmos. Suddenly, there'd be a cosmic up and down, an architecture to reality we never imagined. For now, the axis remains a thorn in the side of modern physics, too stubborn to ignore, too strange to easily explain. It's a reminder that even our most refined maps of the universe might be missing something fundamental, a hidden layer of order or disorder waiting to rewrite the story of everything. We often picture the universe as an endless, three-dimensional expanse, but what if its true shape is far stranger? The geometry of everything isn't just an abstract puzzle. It dictates whether parallel lines eventually collide, whether triangles add up to 180 degrees, and even whether the cosmos could loop back on itself like a cosmic Möbius strip. For decades, scientists have wrestled with three possible shapes for the universe: flat like a sheet of paper, spherical like a globe, or hyperbolic like a saddle. And here's the twist: each scenario would leave its own eerie fingerprints on reality. Start with the simplest candidate, a flat universe. This is the default assumption baked into most textbooks, where space obeys the classic rules of Euclidean geometry. Parallel lines stay forever parallel, and a triangle's angles always sum to 180 degrees. But how do we know it's flat? The cosmic microwave background holds the answer. Tiny fluctuations in this ancient light act like a universal protractor. If the universe were curved, hot and cold spots would appear stretched or shrunken at large scales. Yet when satellites like Planck mapped these patterns, they matched flat geometry with stunning precision. Case closed, not quite, because flatness comes with a cosmic headache. It requires the universe's density to be perfectly balanced, not too thick, not too thin, a condition as unlikely as a pencil balancing on its tip for billions of years. One explanation is inflation, the idea that the early universe expanded exponentially, smoothing out any curvature like stretching a wrinkled balloon. But even inflation can't fully explain why the balance is so exact. Some theorists whisper about multiverses, that our flat universe is just one bubble in a froth of countless others, each with different geometries. Then there's the spherical universe, where space curves gently inward like the surface of a planet. In this scenario, if you traveled far enough in one direction, you'd eventually circle back to your starting point. No edges, no boundaries, just an endless cosmic loop. The catch: a closed universe would need enough matter and energy to warp space-time into this shape, and so far, our accounting falls short. Even adding up all the dark matter and dark energy, the numbers stubbornly point toward flatness. But the wild card is hyperbolic geometry, a universe that curves outward like a saddle, where parallel lines diverge and triangles have angles summing to less than 180 degrees. This would create a kaleidoscopic cosmos, with distant galaxies appearing stretched and distorted in funhouse mirror fashion. While no direct evidence supports this, some anomalies in the cosmic microwave background keep the door cracked open. The real mystery isn't just the shape itself, but what it implies. A flat or hyperbolic universe might stretch forever, cold and infinite. A spherical one could be finite but unbounded, a cosmic Ouroboros. And if space is curved even slightly, it would upend our understanding of everything from dark energy to the ultimate fate of the cosmos. Right now, the data leans toward flat, but with margins of error that leave room for the universe to surprise us. After all, if there's one thing the cosmos loves, it's hiding its true face just beyond our grasp. We know the universe is filled with invisible dark matter, but here's something even stranger: half the ordinary matter, the stuff that makes up stars, planets, and us, has gone missing. Scientists call these lost particles baryons, the building blocks of atoms like protons and neutrons, and according to our best calculations, roughly 50% of them are unaccounted for. It's as if someone took every other brick in the cosmos and hid it in plain sight. So where did they go? Think of it like a galactic treasure hunt. When astronomers tally up all the visible matter, stars, galaxies, gas clouds, it barely scratches the surface. Add in the diffuse gas between galaxies, and we're still coming up short. The leading theory: these missing baryons are lurking in a form so elusive, we've only just begun to detect them. Vast, superheated filaments of gas stretching between galaxies, known as the warm-hot intergalactic medium, or WIM. Imagine a spiderweb of million-degree plasma, so thin and energetic it's practically transparent to our telescopes. Here's why it's been so hard to find. This gas doesn't emit much light, and it's too hot to absorb light passing through it cleanly. Instead, it leaves ghostly fingerprints, subtle distortions in the light of distant quasars as it passes through these cosmic threads. Recent breakthroughs with X-ray telescopes and ultraviolet spectrographs have finally started to map this hidden web, revealing tendrils of ionized oxygen and nitrogen where the missing matter might be hiding. But the plot thickens. Even with these discoveries, the numbers still don't quite add up. Some physicists speculate that a fraction of baryons could be tied up in exotic objects we've overlooked: rogue black holes, faint dwarf galaxies, or even sprawling clouds of cold gas drifting in intergalactic space. Others wonder if the missing matter is locked in dimensions beyond our perception, echoing theories of string theory and higher spatial geometries. The hunt for these lost baryons isn't just academic, it's a crucial piece of the cosmic puzzle. Without them, our models of galaxy formation and cosmic evolution are incomplete, like trying to bake a cake with half the ingredients. Every new telescope trained on the sky brings us closer to solving this interstellar accounting error, one invisible thread at a time. And the real kicker: even after we find them, we'll still have to grapple with the fact that ordinary matter makes up less than 5% of the universe's total mass. The missing baryons are just the tip of the iceberg, a reminder that what we can see might be the least interesting part of the story. Time feels like the most dependable constant, always ticking forward, never stopping. But near the edge of the universe, even this bedrock of reality might unravel. Imagine a place where clocks don't just slow down but stop entirely, where cause and effect dissolve into stillness. Some physicists argue this isn't science fiction. It's a genuine possibility lurking in the farthest reaches of space. The key lies in how time behaves in extreme environments. Near black holes, gravity warps time so severely that to an outside observer, someone falling in would appear frozen at the event horizon forever. Now extrapolate that to the universe's edge, where expansion accelerates galaxies away faster than light. If you could stand at that boundary, you'd witness something eerie. Distant events stretched into infinite slowness, their light redshifted into oblivion. The universe's final moments would play out in a single, never-ending frame, like a movie paused on the last scene. But does time actually end there? One radical theory suggests that in regions where space stretches infinitely thin, time might lose all meaning. Quantum fluctuations, normally buzzing with activity, could freeze solid, locking reality into an eternal instant. No change, no decay, just perfect stasis. This isn't merely the absence of time, it's a state beyond it, where before and after cease to exist. The implications are dizzying. If time stops at the edge, does that mean reality has a boundary where the rules of physics simply give up? Some models propose that in these zones, quantum entanglement, the spooky connection between particles, might persist timelessly, like cosmic flight traps preserving relationships without causation. Others speculate that without time's arrow, entropy could reverse, effectively erasing the concept of disorder. The most unsettling idea, we might already be seeing hints of this. The cosmic microwave background shows regions where temperature fluctuations appear suspiciously smooth, as if time itself ran slower there in the early universe. Could these be fossils of primordial zones where time flickered out? Whether time truly ends or just bends beyond recognition at the universe's edge, one thing's certain: our understanding of reality is built on a dimension that might not be as universal as we think. And that raises a chilling question: if time can stop somewhere, could it happen everywhere? The answer might rewrite not just cosmology, but philosophy itself. Imagine waking up one day to see the sky full of galaxies drifting apart like ships in a storm, not just moving away, but violently ripped apart atom by atom. This isn't just a nightmare scenario, it's a real possibility called the Big Rip, where dark energy, the mysterious force accelerating the universe's expansion, goes from cosmic background player to ultimate destroyer. Here's how it could unfold. Right now, dark energy works like a gentle but persistent push, stretching space between galaxies. But what if that push grows stronger over time? Some models suggest dark energy isn't constant, it might intensify, evolving into something called phantom energy. In this scenario, the expansion wouldn't just speed up, it would accelerate exponentially, eventually overpowering every force in nature. First, galaxy clusters would be wrenched apart, their gravitational bonds no match for the relentless stretching of space. Then, individual galaxies would unravel, stars flung into the void like sparks from a bonfire. But the horror doesn't stop there. As phantom energy grows, even star systems will be torn asunder, planets ripped from their suns, moons from their planets. In the final moments, the very fabric of reality would disintegrate. Atomic bonds would snap, nuclei would split, and eventually, space-time itself might rupture. The universe wouldn't just end with a whimper or a crunch, but with a scream of violent particle-by-particle annihilation. What makes this idea so chilling isn't just the scale of destruction, but the timeline. If the Big Rip is real, calculations suggest it could happen in as little as 22 billion years, a blink of an eye in cosmic terms. Some estimates even place it sooner if dark energy behaves more unpredictably. And unlike other cosmic doomsdays, there'd be no warning signs until it's far too late. One day, gravity would simply lose. Yet the strangest part isn't the destruction, it's what the Big Rip implies about dark energy. We still don't know what it is, only what it does. If it can evolve into something this destructive, then the universe might be sitting on a time bomb, its fate tied to a force we've barely begun to understand. The Big Rip isn't just an ending, it's a reminder that the greatest threats in the cosmos might be hiding in plain sight, woven into the emptiness between the stars. If the Big Rip paints a terrifying portrait of cosmic annihilation, then the Big Crunch offers an equally dramatic, yet eerily poetic alternative. Picture the universe reversing its own birth, galaxies not fleeing apart but falling back together in a slow-motion collapse. Every star, planet, and speck of dust would accelerate toward a single point, growing hotter and denser until reality itself crumples into a fiery singularity. It's the ultimate cosmic reset button, a possibility baked into Einstein's equations over a century ago. This scenario hinges on one critical factor: gravity's endurance. Right now, dark energy dominates, pushing galaxies apart. But what if it weakens over time? Imagine gravity regaining the upper hand, gradually overcoming expansion until the universe's outward breath becomes an inward gasp. Galaxy clusters would merge, colliding in bursts of blue shifted starlight. The cosmic microwave background, now a fading whisper, would grow hotter and brighter as space contracts, like rewinding a film of the Big Bang. The final moments would be apocalyptic. Temperatures would skyrocket, not just melting planets but vaporizing atoms. Protons and neutrons, stable for billions of years, might destabilize under the pressure, dissolving matter into a primordial quark soup. Even black holes, the universe's most indestructible objects, would evaporate in a final burst of radiation known as Hawking evaporation, the end point. A singularity indistinguishable from the one that birthed our universe, a cosmic Ouroboros where the end becomes another beginning. Yet here's the twist: a Big Crunch might not be an ending at all. Some theorists propose it could trigger a new Big Bang, birthing a fresh universe with different physical laws, a cycle of death and rebirth called the Big Bounce. Others suggest the singularity could birth a multiverse, each crunch spawning infinite new realities. It's a hauntingly beautiful idea that destruction isn't final, just transformative. The key difference between the Big Rip and Crunch: one is a story of infinite divergence, the other of ultimate convergence. Both reveal how precariously our universe balances between forces we barely understand, and how even the mightiest structures might someday bow to deeper, darker laws. The Big Freeze isn't just an ending, it's a slow, silent surrender, the universe exhaling its last breath into an eternal chill. Unlike the dramatic collapses or violent rips we've imagined, this fate plays out with eerie tranquility. Picture a cosmos where every star has burned out, every black hole evaporated, and the last remnants of heat bleed away into emptiness. No explosions, no screams, just an endless, uniform darkness colder than the deepest void we can fathom. Scientists call it heat death, and it's not just a poetic metaphor, it's the universe's most probable finale based on the unshakable laws of thermodynamics. It all hinges on entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases, meaning energy disperses and becomes less usable over time. Right now, we live in a universe of contrast: blazing stars against the cold void, galaxies swirling with motion. But entropy guarantees these differences will smooth out, like a cup of hot coffee left to cool in a room. Eventually, every corner of space will reach the same temperature, a hair above absolute zero. No heat gradients mean no work can be done, no stars reignited, no life sustained. The universe becomes a static graveyard of particles so spread out they might as well be alone. But why is this the leading theory? Unlike the Big Rip or Crunch, heat death doesn't rely on speculative physics. It emerges from what we know: energy spreads out, and nothing we've observed reverses that trend. Even dark energy, accelerating expansion, only hastens the process by stretching space so thin that particles lose all connection. Galaxies will fade beyond visibility, their light stretched to wavelengths too long to detect. Black holes, the last bastions of activity, will eventually decay via Hawking radiation, leaving behind only faint whispers of radiation. The timeline, almost unimaginable, 10 to the power of 100 years or more, a number so vast it dwarfs every age of the cosmos up to now. Yet the most unsettling part isn't the timescale, it's the absolute nature of the outcome. A big crunch might recycle the universe, a rip might leave questions, but heat death offers no second acts, no rebirth, no hidden dimensions, just an endless, featureless equilibrium where even time loses meaning. Philosophers debate whether such a state equates to true nothingness, while physicists ponder if quantum fluctuations could ever spark a new beginning. But for now, the math is clear. If the cosmos keeps expanding as it is, the big freeze isn't just possible, it's inevitable. A quiet, pitiless end where the universe doesn't tear apart or collapse, but simply forgets itself. What if our universe is just one page in an infinite cosmic library? That's the spine-tingling premise of the multiverse hypothesis. The idea that our reality might be one of countless others, each with its own unique physics, dimensions, and even versions of you. And the most tantalizing part, the very edge of our universe could be the thin, fraying boundary where these worlds brush against one another, a place where the rules of reality blur into something far stranger. The multiverse isn't just science fiction, it's a serious scientific framework with several competing theories. One version, called eternal inflation, suggests that the rapid expansion of the early universe never truly stopped, it just slowed here, creating a stable bubble we call home. Meanwhile, in other regions, space keeps stretching exponentially, spawning new universes like bubbles in a boiling pot. Each one could have different constants of nature, a universe where gravity is stronger, light slower, or where time runs backward. The edge of our observable universe might mark where our bubble bumps against another, a cosmic shore where the waves of alternate realities lap silently against our own. Then there's the quantum multiverse, born from the many worlds interpretation of quantum mechanics. Every time a particle makes a random choice, like whether it's a wave or a particle, reality splits, creating parallel timelines branching endlessly. Most remain forever out of reach, but what if the universe's boundary is where these timelines physically manifest? A place where every possible outcome of every quantum event exists simultaneously, like an infinite hall of mirrors reflecting every decision you never made. But how could we ever detect these other universes? Some researchers hunt for bruises in the cosmic microwave background, odd temperature patterns that might reveal collisions with neighboring universes in the distant past. Others look for gravitational anomalies or inexplicable voids that defy conventional explanation. The strangest clue, cold spots in the cosmic microwave background, like the one in the constellation Eridanus, which some theorists argue could be the imprint of a universe next door. The most mind-bending possibility, if the multiverse is real, then the edge of our universe isn't an end at all, it's a frontier. A place where the familiar laws of physics dissolve into something richer and more chaotic, where every paradox finds a home in some other reality. It challenges our deepest assumptions, that our universe is all there is, that the constants of nature are fixed, that we're not just one iteration of an endless experiment playing out across the fabric of existence. And that raises a haunting question. If other universes exist beyond our horizon, what unimaginable truths lie just out of reach? The answer might rewrite not just cosmology, but our place in the grand scheme of everything. What if everything you see, the stars, galaxies, even your own hands, is nothing more than an illusion, a shimmering mirage projected from the edge of reality? Welcome to the holographic principle, one of the most radical ideas in modern physics. It suggests that our three-dimensional universe might actually be encoded on a distant, two-dimensional surface, like a cosmic movie screen. And if that's true, the implications for the edge of the universe aren't just strange, they're downright paradigm-shattering. This idea didn't come from nowhere. It sprouted from the study of black holes, those cosmic paradoxes where gravity bends the rules of space and time. In the 1970s, physicist Jacob Bekenstein discovered something startling. A black hole's entropy, a measure of its hidden information, is proportional not to its volume but to the area of its event horizon. In other words, all the data needed to describe what's inside a black hole could fit on its two-dimensional surface. Fast forward a few decades, and theorists like Leonard Susskind and Gerard T. Hooft took this further, proposing that the entire universe might work the same way. Picture it like this. Imagine the universe as a vast, hollow sphere, with every galaxy, star, and atom we perceive actually painted onto the inner surface of that sphere. Just as a hologram encodes a 3D image on a flat sheet, reality as we know it could be a projection from information stored at the boundary of space. That boundary, wherever it is, wouldn't just be a physical edge. It'd be the universe's hard drive, with every event, every particle, every law of physics written into its fabric like lines of code. Now, here's where the edge of the universe gets really wild. If the holographic principle is correct, then what we perceive as depth, the vast distances between stars, the yawning gulfs between galaxies, might just be an elaborate illusion. The true stuff of reality wouldn't be the 3D world we navigate daily, but a shadow play flickering on some distant horizon we can't even see. That means the mysteries we've been grappling with, dark flow, the Great Attractor, even the Big Bang, might not be happening out there at all, but encoded in interactions at the edge we'll never reach. Some physicists take this even further, suggesting the holographic principle could resolve one of cosmology's biggest headaches: how to reconcile gravity with quantum mechanics. In this view, gravity in our 3D world might emerge from quantum interactions playing out on the 2D boundary, like vibrations on a drumhead producing sound in a room. If true, it would mean the edge of the universe isn't just a place, it's the engine of reality itself, humming with calculations that birth space, time, and everything within it. But how could we ever test such a mind-bending idea? Surprisingly, there are clues. Researchers analyzing the cosmic microwave background, the afterglow of the Big Bang, have hunted for signs of pixelation, subtle noise that might betray the universe's true digital nature. Others simulate holographic universes in supercomputers, watching to see if 3D physics can emerge from 2D rules. So far, the evidence is murky but tantalizing, like catching glimpses of a hidden pattern through fog. The holographic principle forces us to ask, is the edge of the universe the end of existence or the foundation of it? Are we the show or just the projection? If this theory holds, then the cosmos isn't just stranger than we imagine. It's stranger than we can imagine, written in a language we're only beginning to decipher. And that leaves us with the most unsettling thought of all. If we're living in a hologram, who or what is holding the projector? In a cosmos filled with hundreds of billions of galaxies, each containing trillions of stars, one question screams louder than the rest: where is everybody? This is the Fermi paradox, the glaring contradiction between the high probability of alien civilizations and our complete lack of evidence for them. But what if the answer isn't hidden among the stars we see, but at the very edge of what we can observe, where the universe's deepest secrets might be silently at work? Consider the Great Filter hypothesis, the idea that some catastrophic barrier prevents civilizations from advancing far enough to colonize the galaxy. Maybe it's self-destruction through war or environmental collapse. Maybe it's a runaway AI or an inevitable cosmic disaster we haven't encountered yet. But there's another chilling possibility. What if the filter isn't behind us but ahead? A wall lurking at the universe's edge, something so insurmountable that no civilization, no matter how advanced, can push past it. Think about the cosmic horizon, the boundary beyond which light hasn't had time to reach us. If the accelerating expansion of the universe locks entire regions of space behind an event horizon, could the same physics be actively preventing the rise of intelligent life elsewhere? Picture a civilization on a planet near that edge, watching the rest of the universe recede faster than they can ever hope to follow. Their night sky would grow darker with each passing eon, galaxies winking out one by one as the void claims them. No interstellar travel, no signals to send, just an inescapable prison of expanding space, or perhaps the filter operates on a deeper level. The laws of physics might subtly change as you approach the universe's edge, making complex chemistry, and thus life, impossible beyond a certain point. Stars could burn out faster, atoms destabilize, or quantum fluctuations grow so violent that stable planetary systems never form. In this scenario, we might not hear from aliens because there are none beyond a thin, habitable shell centered on regions like ours. The universe's rim wouldn't just be empty, it would be sterile. Then there's the darkest twist of all. What if advanced civilizations do reach the edge only to discover something that erases them? A phenomenon so alien it defies comprehension, a cosmic firewall that resets any intelligence that comes too close, like a failsafe built into reality itself. Some theories in quantum gravity even suggest that boundaries between universes could behave unpredictably, unleashing energies or distortions that no technology could withstand. The Fermi paradox might not be about silence, it could be about bottlenecking. The universe's edge wouldn't just be a physical limit, but a great filter testing civilizations on a scale we can't yet fathom. And if that's true, our cosmic loneliness isn't an accident. It's a warning written in the emptiness, hinting that the edge isn't just where the universe ends, but where all ambitions, no matter how grand, might meet their final, indifferent stop. Deep in the constellation Eridanus lies a cosmic anomaly so vast and cold it shouldn't exist, a yawning void stretching nearly 2 billion light-years across, where the afterglow of the Big Bang dips to temperatures that defy explanation. This is the Eridanus supervoid, a blistering cold spot in the cosmic microwave background that's chilled astronomers' spines since its discovery. The numbers alone are staggering. This region is about 70 microkelvin colder than its surroundings, a discrepancy so large that standard cosmology struggles to account for it. If the universe were a pot of soup, this would be an inexplicable cold lump no amount of stirring could dissolve. So what's causing it? The simplest explanation, a lack of matter, doesn't quite fit. Yes, voids exist elsewhere, but none this enormous or this frigid. A void this size would only cool light passing through it by about 20 microkelvin, leaving half the temperature drop unaccounted for. That missing chill has sparked wilder theories, including one that sounds ripped from science fiction. The Eridanus cold spot might be a bruise from a collision with another universe. Here's how that could work. If our universe is part of a multiverse, a froth of bubble universes bumping against each other in higher dimensional space, then a clash with a neighboring bubble could have drained energy from our cosmic microwave background, leaving behind a phantom cold spot. Picture two soap bubbles gently pressing together. The boundary between them would tug at the fabric of both, creating a subtle distortion. In cosmic terms, that distortion might manifest as a region where photons lost energy as they traveled through the warped zone, redshifting into colder temperatures. But not everyone's convinced. Skeptics argue the cold spot could just be a statistical fluke, a cosmic roll of the dice that created an unlikely cold patch in an otherwise uniform background. After all, when you're mapping something as vast as the universe, outliers are inevitable. Others propose less exotic explanations, like an unusually large concentration of dark energy in the void, or even primordial magnetic fields left over from the Big Bang that could have subtly altered the CMB's temperature. The stakes are higher than they seem. If the Eridanus cold spot is evidence of a multiverse, it would be the first tangible clue that our universe isn't alone, a discovery on par with realizing Earth isn't the center of the solar system. Future telescopes, like the European Space Agency's Euclid mission, could settle the debate by mapping the distribution of galaxies within the void. If the supervoid structure aligns with multiverse predictions, it might crack open one of cosmology's biggest mysteries. If not, the cold spot remains a tantalizing enigma, reminding us that even the emptiest corners of space can hold the universe's deepest secrets. And that's the real magic of the Eridanus supervoid. It forces us to question whether the anomalies we dismiss as glitches might actually be messages, whispers from the edge of reality, hinting at truths we're only beginning to imagine. 13.8 billion years, that's the age stamped across astronomy textbooks as the universe's official birthday, calculated from the cosmic microwave background's faint glow. But what if that number is wrong? What if the universe is far older, its true age hidden in the distortions at the very edges of our observations? This isn't just a quibble over dates, it's a crack in the foundation of cosmology that could rewrite the story of everything. Take the Methuselah star, for example. Nestled in the constellation Libra, this ancient sun burns with elements suggesting it's nearly 14.5 billion years old, older than the universe itself according to standard models. At first, scientists dismissed this as impossible, chalking it up to measurement errors. But as more of these too-old stars turned up, along with galaxies in the early universe that looked suspiciously mature, a troubling question emerged: could our cosmic timeline be missing a few billion years? The answer might lie in the universe's shadowy frontiers. When we peer at the most distant galaxies, their light warped by eons of travel, some appear to have formed structures too quickly for the Big Bang's timeline. These cosmic elders shouldn't exist, like finding a fully grown tree in a forest that supposedly sprouted yesterday. One radical explanation: the universe underwent a silent phase before the Big Bang, a stretch of time where space existed in a cold, empty state before something triggered the explosive expansion we call inflation. In this scenario, the Big Bang wasn't the true beginning, just the moment our observable universe flickered to life. Then there's the cosmic microwave background itself. Tiny anomalies in its temperature patterns, subtle swirls and asymmetries, could be echoes of events predating the Big Bang, like scars from a collision with another universe. If true, our 13.8 billion years might only count the age of this cycle, while the cosmos itself could be immeasurably older, cycling through births and deaths we can't yet fathom. The stakes couldn't be higher. If the universe is older, then dark energy's acceleration might not be constant but fading, a relic of some earlier epoch. The hunt for alien life would need to account for civilizations that might have arisen billions of years before Earth even formed. Even the nature of time itself would come into question. Is it a straight line or a loop we've only glimpsed a fraction of? For now, the debate rages on, with every telescope trained on the cosmos edge serving as both time machine and detective. Whether the universe's true age stays locked at 13.8 billion or stretches into uncharted epochs, one thing's clear: the deepest mysteries aren't just written in the stars. They're written in the wrinkles of time itself. We've all felt the thrill of pressing the gas pedal a little too hard. That momentary rush before reality reminds you speed has consequences. Now imagine the universe doing the same, but with no brakes at all. That's the terrifying premise behind phantom energy, a hypothetical flavor of dark energy so destructive it could turn cosmic expansion into an unstoppable runaway train. Dark energy already puzzles scientists. It's the mysterious force accelerating the universe's expansion, making galaxies flee from each other faster every second. But what if it's not a steady push? Phantom energy suggests dark energy's strength might increase over time, its density growing as space stretches. Picture a spring that doesn't weaken when pulled, it tightens, storing more energy the farther it's stretched. Now replace that spring with the fabric of spacetime itself. The consequences escalate quickly. First, galaxy clusters would be torn apart, their gravitational bonds no match for the mounting pressure. Next, individual galaxies would unravel, stars ripped from their orbits like petals in a hurricane. But the true horror comes in the final moments. As phantom energy's density approaches infinity, it wouldn't just separate celestial objects, it would shred spacetime itself. Atomic nuclei would disintegrate, protons torn apart in a process cosmologists grimly call the Big Rip. The universe wouldn't just end, it would be unmade, particle by particle, in a final scream of phantom energy's triumph. Here's where it gets even stranger. Unlike other cosmic doomsdays, the Big Rip wouldn't wait for the distant future. If phantom energy exists, calculations suggest it could dominate within 22 billion years, a heartbeat in cosmic time. Some models even hint it could happen sooner if dark energy's equation of state, a parameter describing its pressure-to-density ratio, dips below a critical threshold. That's the real nightmare. We might already be on this path with no way to detect it until it's too late. Yet phantom energy isn't just a villainous plot twist, it's a mirror held up to our ignorance. We still don't know what dark energy is, let alone how it might evolve. Could it transition into this catastrophic phase, or is the universe's expansion destined to gentle into a silent freeze? The answer might lie in the most violent corners of quantum physics, where negative energies and unstable vacuums flirt with reality's destruction. One thing's certain, if phantom energy is real, the edge of the universe isn't just a boundary, it's a countdown clock. And every galaxy racing away from us carries the same silent warning. Some forces don't just shape the cosmos, they might erase it. At the very edge of reality, where galaxies fade into the void and the known laws of physics start to crack, spacetime itself might dissolve into something far stranger. A seething, turbulent ocean of chaos known as quantum foam. Picture the fabric of the universe not as a smooth, unbroken sheet, but as a stormy sea with tiny bubbles of space and time constantly popping in and out of existence. These aren't just metaphors. According to some theories in quantum gravity, this froth could be the true nature of reality at the smallest scales. But what happens when we zoom out to the cosmos' farthest reaches? Could the extreme conditions at the universe's edge turn this microscopic turbulence into something vast and visible? The idea of quantum foam comes from merging quantum mechanics with general relativity, two pillars of modern physics that famously refuse to play nice. On tiny scales, quantum uncertainty suggests that empty space isn't empty at all. Instead, it's a frenzy of virtual particles appearing and vanishing in fractions of a second, borrowing energy from nothingness before returning it. Now imagine spacetime itself participating in this dance. Tiny, Planck-length regions might warp, twist, or even tunnel into temporary wormholes, creating a foam-like structure where the concepts of here and now lose all meaning. Normally, this frenzy is too small to notice, hidden beneath the smooth surface of our everyday experience. But at the universe's edge, things get weird. The extreme gravitational forces near cosmic horizons, places where space stretches thin or expansion accelerates, could amplify these quantum fluctuations to macroscopic scales. Instead of microscopic bubbles, you might get vast, unstable pockets where spacetime's structure flickers like a glitching hologram. Light traveling through these regions could twist unpredictably, creating bizarre optical effects. Time might stutter or even flow backward in localized patches. And if the foam becomes turbulent enough, entire regions of space could momentarily disconnect from the rest of reality, like islands adrift in a choppy sea. Some theories suggest this quantum turbulence could explain anomalies we've already detected, like the way certain cosmic rays arrive with impossibly high energies, or why some distant quasars flicker in patterns that defy smooth spacetime. Others speculate that if we could peer past the observable universe's boundary, we wouldn't see a clean edge but a fractal storm of dissolving causality where cause and effect scramble into nonsense. It's a place where black holes might spontaneously form and evaporate, where dimensions fray like worn fabric, and where the universe itself might be constantly rewriting its own rules. Yet the most unsettling implication isn't just about the edge, it's about us. If space-time is fundamentally foamy, then the smooth, predictable universe we experience might be an illusion, a statistical average of countless chaotic fluctuations. Like the surface of a calm pond that, when examined drop by drop, reveals itself to be a crashing waterfall, the edge simply throws this chaos into sharp relief, forcing us to confront the possibility that reality's foundations are far wilder than we ever imagined. And if that's true, then the universe isn't just stranger at its boundaries, it's revealing its true, frenzied face. Deep in the constellation Eridanus lies a cosmic cold spot so vast and unexplained it could rewrite our understanding of reality. This eerie anomaly in the cosmic microwave background, dubbed the cold spot, spans nearly 2 billion light-years, registering 70 microkelvin colder than its surroundings. At first glance, it might seem like just another imperfection in the universe's afterglow, but its size and chill defy every expectation. Standard cosmological models can't fully account for it, leaving scientists wrestling with a tantalizing question. Is this a cosmic defect, a statistical fluke, or something far wilder, like a collision with another universe? To grasp why this cold spot is so perplexing, picture the cosmic microwave background as a snapshot of the infant universe frozen in time. Tiny temperature fluctuations in this ancient light reveal the seeds of all future structure galaxies, clusters, and voids. But the Eridanus cold spot isn't just a minor ripple, it's a yawning chasm of coldness that shouldn't exist under normal conditions. One theory suggests it's a supervoid, an unusually sparse region where the lack of matter causes light passing through to lose energy, creating a slight cooling effect. But here's the catch, even the largest known voids only explain half the temperature drop. The rest remains an enigma. That missing chill has sparked radical alternatives. Some theorists propose the cold spot could be a cosmic texture, a topological defect in space-time left over from the universe's fiery birth. Like a wrinkle frozen in the fabric of reality, these textures would warp the surrounding space, subtly altering the CMB in ways that might mimic the cold spot signature. Others suggest it's evidence of a bubble universe collision, a gravitational bruise from when our cosmos bumped against another in the multiverse. Imagine two soap bubbles brushing together in a froth of universes. The boundary between them could leave behind a telltale cold imprint in the CMB, a fossilized handshake from another reality. The implications are staggering. If the cold spot is truly a multiverse fingerprint, it would be the first tangible evidence that our universe isn't alone, a discovery on par with Copernicus realizing Earth wasn't the center of the solar system. Future telescopes like the European Space Agency's Euclid mission aim to map the distribution of galaxies within the cold spots region, searching for structural oddities that could tip the scales toward one theory or another. Until then, the cold spot remains one of cosmology's most tantalizing maybes, a silent siren call from the edge of the knowable. Yet the most haunting possibility isn't that it's proof of the multiverse, it's that it might be something even stranger, a glitch in the cosmic code we haven't begun to decipher. Whether defect, collision, or statistical mirage, the Eridanus cold spot forces us to confront how little we understand about the universe's deepest architecture. And that's the real chill. Some mysteries don't just push the boundaries of science, they lurk just beyond them, waiting to upend everything we think we know. Imagine spinning a top and watching it wobble. Now picture that same instability writ across the cosmos itself. For decades, astronomers assumed the universe expanded evenly in all directions, a perfectly symmetrical growth from the Big Bang. But mounting evidence suggests something far stranger might be happening. The entire universe could be rotating, twisting space-time on scales so vast it redefines our understanding of cosmic edges. The first hints came from studies of distant galaxy clusters, When researchers mapped their motion across the sky, they noticed an eerie pattern. Clusters on one side of the universe seemed to move slightly faster than those on the opposite side, as if caught in a gentle current. At first, scientists dismissed this as a fluke, maybe uneven dust distribution or measurement errors. But as more surveys confirmed the anomaly, including subtle imprints in the cosmic microwave background, the unthinkable became plausible. Could the universe have a preferred axis of rotation, a cosmic whirlpool billions of light-years wide? If true, the implications would shatter foundational assumptions. A rotating universe would violate the cosmological principle, the idea that the cosmos is uniform and isotropic at large scales. Instead of a featureless expansion, we'd live in a spinning colossus with a distinct orientation, like a grain of sand trapped in amber swirls. The rotation source is even more puzzling. Some theorists point to primordial conditions, a lopsided torque imparted during the Big Bang itself, when quantum fluctuations might have tipped the scales. Others speculate it's the gravitational tug of something beyond our universe, a neighboring reality warping ours like a passing ship, distorting the water around it. The most mind-bending consequence: rotation could redefine the universe's edge. In a static cosmos, the boundary is where expansion outpaces light. But if space itself is churning, that edge might behave more like the rim of a spinning top, a zone where centrifugal forces stretch the fabric of reality, creating exotic conditions where time and gravity twist unpredictably. Light traveling from these warped frontiers could arrive scrambled, carrying distorted clues about the universe's true shape, yet skepticism remains. Critics argue the apparent rotation could be an illusion caused by uneven dark energy distribution or undiscovered systematic errors in our observations. The debate hinges on future missions like the European Space Agency's Euclid telescope, which will map billions of galaxies to hunt for definitive proof of cosmic spin. Whether real or phantom, the rotation hypothesis forces us to confront an unsettling possibility. The universe might not just be expanding, it could be dancing, its edges whirling to a rhythm we're only beginning to hear. And if that's true, the greatest mysteries may not lie in the void beyond, but in the slow, silent pirouette of everything that exists. If dark matter had a favorite hiding spot, it would be at the very edges of galaxies, forming vast, invisible cocoons that defy everything we know about gravity. These ghostly structures, called dark matter halos, stretch far beyond the visible starlight, enveloping galaxies in mysterious gravitational embrace. But here's the puzzle. Why does dark matter, the universe's most elusive substance, cluster in these distinct halo-like formations instead of blending evenly through space? The answer might rewrite our understanding of cosmic architecture. Take our own Milky Way as an example. If you could see its dark matter halo, it would dwarf the sparkling spiral of stars we recognize. This halo extends nearly 10 times farther than the galaxy's visible disk, a sprawling web of unseen mass that bends the paths of stars and light passing through it. Yet despite its enormity, dark matter refuses to clump at the galaxy's center like ordinary matter. Instead, it lingers at the fringes as if repelled by some unseen force. This behavior is so consistent across the cosmos that halos have become a universal signature, yet no one fully understands the rules governing their shape. One leading theory points to dark matter's cold nature, meaning its particles move sluggishly compared to the speed of light. This sluggishness would let gravity draw it into loose, extended structures rather than tight knots. But simulations reveal something stranger. Dark matter halos aren't smooth spheres. They're lumpy, with dense subhalos swirling inside like raisins in dough. Some of these subhalos might even host their own tiny galaxies, invisible except for the gravitational tug they exert. It's as if dark matter builds its own shadow universe, a hierarchy of hidden structures lurking just beyond our sight. The real shock came when astronomers realized these halos don't match predictions. According to the standard model of cosmology, dark matter should pile up most densely at a galaxy's core. Instead, many halos show a chord profile, their density plateaus toward the center, almost as if something's pushing particles outward. Some scientists speculate this could hint at dark matter's true nature. Perhaps it interacts with itself through unknown forces, or maybe it's not a single particle but a mix of strange components with conflicting behaviors. Then there's the puzzle of missing halos. Our models predict countless small dark matter clumps should orbit large galaxies, yet we've found far fewer dwarf galaxies than expected to match them. Are these halos truly empty, or is dark matter somehow evading detection? One provocative idea suggests that early radiation from newborn stars might have heated and dispersed dark matter in small halos, preventing galaxies from forming inside them. The mystery deepens when we look at the universe's largest scales. Galaxy clusters, colossal cities of galaxies bound together by gravity, also sit within titanic dark matter halos. But these halos bend light so severely that they act as cosmic lenses, distorting the images of background galaxies into surreal arcs. By mapping these distortions, astronomers have uncovered halos that are oddly flattened or elongated, defying the spherical symmetry our models predict. Could this be evidence of dark matter interacting with unseen cosmic filaments, or even something more exotic like primordial black holes woven into the halo's fabric? Every unanswered question about dark matter halos underscores how little we grasp about the invisible scaffolding of the cosmos. They're not just curiosities, they're cosmic fingerprints holding clues to dark matter's identity and the universe's hidden blueprint. And until we crack their code, we're like sailors navigating by the stars, guided by visible lights, oblivious to the vast, uncharted depths beneath us. Black holes have long been the universe's ultimate vaults, cosmic prisons where matter, light, and even the laws of physics seem to vanish without a trace. But what if these gravitational monsters aren't just swallowing stars? What if they're erasing the very fabric of reality itself? That's the heart of the black hole information paradox, a quantum riddle so profound it threatens to unravel our understanding of how information behaves at the universe's edge. Here's the problem in a nutshell. Quantum mechanics insists that information, the fundamental blueprint of every particle's properties, can never truly be destroyed. It might get scrambled or hidden, but it's always preserved, like a cosmic ledger keeping track of every event. But black holes defy this rule. When matter falls into one, it's crushed into a singularity, a point of infinite density where space-time breaks down. According to Einstein's general relativity, that information is lost forever, locked behind an event horizon that even light can't escape. The paradox deepens when we consider what happens when black holes slowly evaporate via Hawking radiation. Stephen Hawking showed that black holes aren't entirely black. They emit faint radiation over eons, eventually shrinking to nothing. But here's the catch: Hawking radiation appears random, carrying no trace of the information that fell in. If the black hole vanishes, where did the information go? It's like burning a book and claiming the ashes contain no hints of its contents, except quantum mechanics says that's impossible. This isn't just a philosophical quandary. If information can vanish without a trace, it undermines the predictability of the entire universe. The past, present, and future become untethered from cause and effect, like a movie reel with random frames snipped out. Some physicists, like Leonard Susskind, argue the information isn't lost, it's encoded on the black hole's event horizon, a holographic fingerprint scrambled beyond recognition. Others propose wilder solutions, like black holes tunneling into baby universes, carrying the information elsewhere like cosmic teleportation. Now imagine scaling this paradox to the universe's edge. If black holes, localized points of infinite gravity, can threaten information's survival, what happens at the boundary of everything? Regions where space-time stretches infinitely thin, where expansion outpaces light itself. Some theories suggest these edges could act like cosmic event horizons, trapping information in unreachable pockets of reality. Light and data racing toward the boundary might redshift into oblivion, their signals fading like whispers in a hurricane. The terrifying implication: if information can't cross the universe's edge, then the fate of everything, every star, every civilization, every particle might be eternal isolation. Not destruction, but dissolution, like ink dissolving in an infinite ocean. The black hole information paradox isn't just about singularities. It's a warning that the universe's frontiers might be places where reality itself starts to forget. And that raises a chilling question. If even information can't escape the edge, are we truly alone, or just cut off from something or someone beyond? Deep in the cosmos, trillions of ghostly particles pass through your body every second, leaving no trace, yet they might hold the keys to understanding the universe's most distant frontiers. These are neutrinos, nature's most elusive messengers, born in the hearts of stars, supernova, and even the Big Bang itself. So light they barely interact with matter, they travel billions of light years unimpeded, carrying secrets from the edge of reality straight to our detectors. But here's what's truly astonishing. A faint, ancient sea of these particles, the cosmic neutrino background, permeates all of space, and decoding its whispers could reveal truths about the universe no telescope can see. The cosmic neutrino background is the universe's oldest unsent letter, written when the cosmos was just 1 second old. Picture the Big Bang's aftermath, a seething plasma so dense that even neutrinos, which normally slip through walls like ghosts, were trapped. As the universe cooled, these particles broke free, streaming outward in all directions. Today, that primordial neutrino fog still lingers, cooled by expansion to just 1.9 degrees above absolute zero. Detecting it is like trying to hear a whisper in a hurricane, but if we could, it would show us the universe before galaxies or stars even existed. Why does this matter? Neutrinos interact so weakly that they've traveled uninterrupted since their birth, preserving a snapshot of the cosmos in its infancy. Unlike the cosmic microwave background, which shows us the universe 380,000 years after the Big Bang, neutrinos offer a glimpse millions of times earlier. Their subtle patterns could reveal hidden forces that shaped cosmic expansion, or even cracks in our understanding of particle physics. Some theories suggest neutrino oscillations. Their eerie ability to change flavors mid-flight might hint at extra dimensions or unknown particles lurking just beyond our models. But the real magic happens at the universe's edge. High-energy neutrinos blasted across space by supermassive black holes or colliding galaxies act as cosmic probes. When they reach us, their paths trace back to sources so distant their light will never arrive. Ice Cube, a detector buried in Antarctic ice, has already caught neutrinos with energies 1,000,000 times greater than those from our Sun, some possibly hurled from galaxies beyond the observable horizon. These ultra-high-energy messengers might carry clues about regions of space we'll never see directly, like echoes from a shore we can't visit, the ultimate prize. Neutrinos could be our only window into phenomena hidden by cosmic event horizons. Black holes might trap light, but neutrinos, barely noticing gravity's pull, could slip free, carrying encoded details of their violent birth. Even dark matter, the universe's most mysterious substance, might betray its presence by subtly altering neutrino flavors as they journey through galaxy clusters. Yet the challenge is staggering. To catch these phantoms, scientists build detectors the size of cities, like Super Kamiokan's colossal water tank in Japan, or the future deep underground neutrino experiment's 50,000-ton liquid argon chamber. Each experiment pushes technology to its limits, hunting for the faintest flashes of light or bubbles in liquid that signal a neutrino's fleeting touch. What keeps researchers going is the tantalizing possibility that neutrinos might rewrite cosmology. Their masses, still not precisely known, could explain why the universe has more matter than antimatter. Their behavior might reveal why galaxies cluster differently than our models predict, and their background hum, if ever mapped in detail, could expose quantum ripples from the Big Bang itself, whispers from the moment time began. In the end, neutrinos are more than cosmic curiosities. They're shadowy couriers from the farthest reaches, carrying stories we're only beginning to decode. Every one that passes through you is a thread woven into the universe's grand tapestry, a silent reminder that the deepest truths often hide in the smallest, most fleeting signals. And if we learn to listen, they might just tell us how the story ends. The universe isn't just a scattered collection of galaxies, it's a vast, intricate tapestry, woven together by threads of dark matter and gas stretching billions of light years. Scientists call this the cosmic web, and while we've mapped its broad strokes closer to home, its outermost fringes remain a labyrinth of mysteries. These distant filaments, barely visible against the void, aren't just faint echoes of structure, they're cosmic anomalies challenging our understanding of how the universe builds itself. Picture the cosmic web as a colossal neural network, with galaxies clustering along glowing threads like beads on a string. At the heart of this web, near massive galaxy clusters, gravity pulls matter into dense knots. But venture toward the edge and the filaments grow sparse, wispy, almost ghostly. Some stretch so far they defy expectations, tenuous bridges connecting voids of near nothingness. The oddest part, these faint tendrils shouldn't exist in such pristine form. According to simulations, the violence of cosmic evolution, galactic collisions, supernova explosions should have torn them apart long ago. Yet there they are, haunting the frontiers like cosmic fossils. One theory suggests these fragile filaments are relics from the universe's infancy, regions where matter avoided the chaos of clustering until recently. Another proposes they're fed by dark matter currents, rivers of invisible particles streaming through the void, sculpting gas into delicate ribbons. But the most tantalizing possibility, these filaments might be signatures of something darker. Some models hint that certain types of dark matter, maybe even hypothetical, fuzzy, or warm dark matter, could leave behind faint, stretched-out trails as they resist clumping. If true, the cosmic web's edges aren't just architectural oddities, they're a hidden ledger of dark matter's true nature. Then there's the puzzle of what lights them up. Normally, filaments glow faintly with heated gas, but at the universe's edge, some flicker with unexpected brilliance. Could abandoned dwarf galaxies, too dim to spot directly, be hiding along these threads? Or are we seeing the glow of primordial gas, untouched since the Big Bang, finally collapsing under its own weight? The answer might lie in the way these filaments warp light. Like cosmic fiber optic cables, they bend the paths of distant quasars, creating subtle distortions that hint at their mass and structure. Yet the greatest challenge these filaments pose isn't just their existence, it's what they say about our models. Simulations like the Millennium Run predict how the cosmic web should grow, but none perfectly replicate the fragile giants we observe. Some filaments stretch longer than expected. Others twist in ways that suggest unseen forces at work. Are we missing a key ingredient in the recipe of cosmic evolution? Could there be a shadowy interaction between dark matter and dark energy, playing out only in the universe's loneliest reaches? Every unanswered question about these filaments is a crack in the foundation of cosmology. They're not just quirks of the cosmos, they're stress tests for our understanding of gravity, structure formation, and the invisible forces shaping everything. And as telescopes like the James Webb Space Telescope peer deeper into the cosmic web's fringes, one thing becomes clear: the universe's edges aren't just boundaries. They're mirrors reflecting back all the things we still don't know. We think of space as an endless, three-dimensional expanse, but what if the universe isn't just big but strangely shaped? Imagine walking in a straight line through space, only to end up right back where you started, like an ant crawling across the surface of a donut. This might sound like science fiction, but it's a serious possibility in cosmology. the universe could have hidden twists, loops, or even holes in its geometry, warping reality on scales so vast we haven't noticed yet. This puzzle is called topology, the study of shapes and how they connect. Normally, we assume the cosmos is simply connected, meaning any loop you draw in space can shrink smoothly to a point without snagging on weird folds. But what if it's not? Some theories suggest the universe could be multiply connected, folding back on itself in ways that create repeating patterns. A donut-shaped or torus universe, for example, would mean that if you peered far enough in one direction, you'd see the back of your own head, light having looped the entire cosmos. The wildest part, we might already have clues. The cosmic microwave background, the afterglow of the Big Bang, acts like a cosmic fingerprint for topology. If space were twisted into a donut or another complex shape, we'd expect to see matching patterns of hot and cold spots repeating across the sky, like hall of mirror reflections. In the early 2000s, researchers thought they'd spotted such echoes in satellite data, hinting at a universe folded into a dodecahedron, a 12-faced shape where opposite faces connect. But later studies muddied the waters, leaving the question unresolved. Then there's the small universe hypothesis. If the cosmos is finite and multiply connected, it could be far smaller than we think, just wrapped so cleverly it appears infinite. Light would have taken multiple laps around the universe since the Big Bang, making distant galaxies seem farther away than they truly are. Imagine living on a Pac-Man board. The screen seems endless because exiting one side teleports you to the other, but in reality, it's a tiny, repeating grid. If true, the night sky's vastness might be the ultimate optical illusion. But why would the universe have such a bizarre shape? One answer lies in quantum fluctuations during inflation, the universe's explosive early growth spurt. Tiny knots in spacetime could have stretched into cosmic-scale twists, leaving behind a knotted topology. Some string theorists even propose that extra dimensions, curled up so small we can't detect them, might influence the overall shape of our 3D reality, like unseen folds in a crumpled sheet of paper. Of course, not everyone's convinced. Skeptics argue that if the universe were donut-shaped, we'd have found clearer repeating patterns by now. Others suggest that any detectable topology would require the universe to be improbably small, contradicting measurements of its flatness. But the hunt isn't over. Upcoming telescopes like the European Space Agency's Euclid mission could scour the cosmic microwave background for faint, repeating swirls, ghostly signatures of a universe that's not just expanding but knotted. The truth is, we're like flatlanders living on the surface of a balloon, oblivious to the greater shape until we learn to look beyond our dimensions. Whether infinite or ingeniously folded, the universe's topology isn't just a math puzzle, it's a question about the very fabric of reality. And if we one day prove it's curved, looped, or even knotted, it won't just change how we see space. It'll redefine where and what we truly are. Stretching across the cosmic microwave background like a faint scar, the cold spot in the constellation Eridanus might be more than just a cosmic oddity. It could be a bruise from a collision with another universe. Picture two soap bubbles brushing against each other in a froth of realities, each carrying its own laws of physics, its own history. Where they touch, space-time itself might warp, leaving behind subtle imprints that linger for billions of years. This is the tantalizing premise behind bubble universe collisions, a theory that our cosmos isn't alone but part of a vast multiverse, where neighboring realities occasionally bump into one another with consequences we're only beginning to decipher. The idea springs from eternal inflation, a model where our universe is just one bubble in an endlessly expanding cosmic foam. Beyond our observable horizon, other bubbles, other universes might be inflating too, each with different fundamental constants. Most will forever drift apart, but occasionally, two bubbles could collide, sending shockwaves rippling through both. the aftermath, a telltale signature in the cosmic microwave background, the faint afterglow of the Big Bang that blankets the sky. Researchers have scoured this ancient light for hints of these collisions, hunting for anomalous patterns, circular distortions, unusual temperature gradients, or asymmetries that defy conventional explanations. The most famous candidate is the Eridanus cold spot, a region nearly 2 billion light-years wide that's significantly cooler than its surroundings. While some argue it's just a vast supervoid, a sparse region where the lack of matter cools passing photons, others point out that the temperature drop is too extreme for that alone. A bubble collision, though the physics fits. When universes collide, the energy released could create a localized dent in space-time, a region where light loses extra energy as it climbs out of the gravitational well, redshifting into colder temperatures. It's like rolling a marble up a hill. The steeper the slope, the more speed it loses. But the smoking gun would be more specific, concentric rings of temperature variation, like ripples from a pebble dropped in a pond. These would mark the collision's epicenter, a frozen snapshot of the moment our universe brushed against another. So far, no such rings have been definitively found, but anomalies in the Planck satellite's data keep theorists hopeful. Some even speculate that multiple collisions could have occurred, layering subtle patterns atop one another, waiting for sharper instruments or smarter algorithms to tease them apart. The implications are staggering. If these marks are real, they'd be the first empirical evidence of a multiverse, proof that our universe is just one page in an infinite cosmic library. Each collision imprint would encode clues about the other universe's properties, its dimensionality, its physical laws, even its history. Was it a universe where gravity was stronger or where time flowed backward? The cold spot could be a cipher we're only beginning to crack, yet skeptics urge caution. The universe is a noisy place, full of random fluctuations that can masquerade as signals. What looks like a collision scar might just be a statistical fluke, a cosmic Rorschach test where we're seeing patterns that aren't really there, the only way to know. Build better maps. Future observatories like the Simons Observatory or SIMBS-4 will scan the sky with unprecedented precision, hunting for the faintest whispers of these ancient encounters. Whether the cold spot is a true multiverse bruise or just a cosmic mirage, the search itself rewrites what it means to explore. We're no longer just peering at stars, we're reading the wrinkles of reality, searching for fingerprints left by universes we'll never see. And that raises a haunting question. If we do find them, how many other collisions have gone unnoticed, hidden in the noise of creation? The edge of our universe might not be a boundary at all, but a mosaic of scars, each one a story waiting to be told. Picture waking up in total darkness, no body, no past, just a lone consciousness floating in the void, conjuring an entire universe from fragments of random memory. This isn't a nightmare, it's the Boltzmann brain paradox, one of the most unsettling thought experiments in cosmology. It forces us to ask, what if the vast universe we perceive is just a fleeting hallucination, a glitch in an infinite void where self-aware minds blink into existence by sheer accident? The paradox springs from thermodynamics, specifically Ludwig Boltzmann's groundbreaking work on entropy, the idea that disorder always increases over time. In an infinitely old or infinitely large universe, even the most improbable events must occur eventually. Given enough time, atoms jostling in the void could randomly arrange themselves into a fully formed brain, complete with fabricated memories of a life that never happened. Statistically, it's more likely for a single, disembodied brain to spontaneously form than for an entire, ordered universe like ours to emerge from chaos. So why do we find ourselves in a cosmos full of galaxies and history, rather than as isolated minds drifting in nothingness? Here's where it gets even stranger. The same physics that predicts Boltzmann brains also undermines our trust in reality itself. If self-aware entities are more likely to arise as random fluctuations than as products of evolution in a stable universe, then the odds suggest you are probably one of those fluctuations. Every memory, every sensation, the screen in front of you, the weight of your body, could be an elaborate fiction, a hallucination that lasts for just a fraction of a second before dissolving back into the void. Critics pounce on this idea with fierce resistance. For one, Boltzmann brains require absurdly precise conditions. Even in an infinite universe, the probability of a fully functional brain assembling by chance is so infinitesimal that it makes winning the lottery every second for 1 billion years look like a safe bet. Some physicists argue that if such minds were more common than real observers, we'd expect to wake up mid-fluctuation surrounded by nonsensical, fragmented perceptions, not the coherent, consistent reality we experience. Yet the paradox refuses to die because it's tangled up with deeper questions about the cosmos. If the universe is truly infinite or eternal, shouldn't all possible configurations of matter arise, no matter how improbable? And if our universe is just one bubble in an inflationary multiverse, wouldn't most conscious entities find themselves in the emptiest, longest-lasting regions where entropy reigns and Boltzmann brains outnumber evolved life? One escape route lies in the very nature of time. Quantum gravity theories suggest time itself might emerge from a more fundamental layer of reality, preventing true, infinite time scenarios where Boltzmann brains become inevitable. Others propose that consciousness can't arise from random fluctuations at all. It might require specific, structured interactions that only a universe like ours can provide. But the most haunting implication isn't just about brains in voids. It's about the fragility of knowledge. If randomness can fabricate minds, then science itself, built on the assumption that our observations reflect objective reality, rests on shaky ground. The Boltzmann brain paradox doesn't just question the universe, it questions whether we can trust any of our conclusions about it. So where does that leave us? Perhaps the answer isn't in dismissing the paradox, but in letting it refine our theories. The mere absurdity of Boltzmann brains might be a clue that our universe isn't infinite or eternal in the ways we've assumed. Or maybe it's a sign that consciousness is far rarer and more precious than physics alone can explain. Either way, the paradox lingers like a shadow at the edge of cosmology, a reminder that the universe's greatest mysteries might not be out in the stars, but in the very nature of existence itself. Gravitational waves aren't just cosmic messengers, they might be our only hope for eavesdropping on the edge of the universe itself. These faint ripples in space-time, first detected in 2015, usually tell stories of colliding black holes or merging neutron stars. But if we listen carefully to their quietest frequencies, they could reveal something far stranger, whispers from realms beyond our cosmic horizon, places where light itself will never reach us. Here's how it works. When massive objects like black holes spiral toward each other, they churn space-time like spoons stirring honey, sending out gravitational waves that travel at the speed of light. Most of these signals come from events within our observable universe, but some theorists speculate that ultra-low frequency gravitational waves, ones with wavelengths so long they take years or even centuries to oscillate, might carry imprints from beyond the horizon. These wouldn't be from stellar collisions, but from primordial phenomena in the universe's earliest moments, or even echoes of structures lurking in the unobservable darkness. The most tantalizing possibility, these waves could be tracing the outline of a multiverse. If our universe collided with another during inflation, the explosive expansion fractionally after the Big Bang, the shock waves might have left behind a specific pattern of gravitational waves like fingerprints on glass. Future observatories like the Laser Interferometer Space Antenna LISA could detect these ultra-low frequency ripples, potentially uncovering evidence that our cosmos isn't alone. It's akin to standing in a sealed room and feeling vibrations through the walls. You can't see the source, but you know something's out there. But the edge's gravitational waves might hold darker secrets too. If spacetime itself dissolves into quantum foam at the boundary, a turbulent sea of virtual black holes and wormholes, it could generate a constant, hissing static of high-frequency gravitational waves. Imagine tuning a radio to a dead channel and hearing not white noise, but the fizzing of spacetime's underlying structure. Detecting this foam would revolutionize physics, proving that gravity isn't smooth and continuous, but pixelated and chaotic at the smallest scales. Then there's the eerie case of ghost black holes, primordial ones formed in the universe's first second, now lurking beyond our horizon. Though invisible, their gravity could subtly warp passing gravitational waves, stretching or compressing them like funhouse mirrors. By studying these distortions, we might indirectly map the distribution of these shadowy behemoths, charting a hidden geography of the unseen cosmos. The challenge, of course, is separating signal from noise. Gravitational wave detectors must contend with everything from seismic tremors to passing trucks, let alone the cacophony of merging galaxies. But as technology advances, we're inching closer to unlocking frequencies that could carry messages from the universe's farthest shores. Every new ripple decoded is like finding a bottle washed up on a beach, cracked open. It might contain a map to realities we've never dared imagine. And that's the real magic of these space-time ripples. They don't just tell us where the universe has been. They might be the only voices that can reach us from places we'll never see, singing songs of edges beyond edges, of boundaries that shift and truths that shimmer just out of reach. At the ragged edge of the observable universe, where galaxies fade into darkness and the laws of physics start to fray, lies the ultimate cosmic riddle, not just how the universe behaves, but how it will end. For centuries, humanity has gazed at the stars and wondered about our final destiny. But modern cosmology reveals that the answer might be written in the empty spaces between galaxies, in the silent pull of dark energy, and in the hidden geometry of spacetime itself. Will the cosmos tear itself apart in a violent big rip, collapse back into a singularity, or fade into an eternal, frozen stillness? The edge holds clues to all these possibilities, acting as both a window and a warning. Consider the accelerating expansion we see today, galaxies speeding away faster as dark energy dominates gravity's grip. If this continues unchecked, the universe's fate might be the big freeze, a slow, silent dissolution where stars burn out, black holes evaporate, and space stretches so thin that even atoms are ripped apart by the relentless expansion. But the edge complicates this picture. Regions beyond our cosmic horizon are already lost to us forever, their light never reaching Earth. If dark energy evolves into something stronger, phantom energy, those distant frontiers could be the first to unravel, space-time itself shredding like tissue paper in a hurricane. Yet there's a haunting alternative. What if the universe isn't destined for cold oblivion, but for a fiery rebirth? The Big Crunch scenario suggests that gravity could one day reverse expansion, pulling everything back into a singularity so dense it triggers another Big Bang. The edge plays a bizarre role here too. Some theories propose that the universe's shape, whether flat, spherical, or saddle-like, could determine its fate. A closed, spherical cosmos might collapse under its own weight, while an infinite, flat one could expand forever. But what if the edge isn't a true boundary but a fold? In a donut-shaped universe, the expansion might eventually loop back on itself like a snake eating its tail. Then there's the wild card, vacuum decay. Quantum theory suggests our universe might not be in its most stable state. A single random fluctuation, perhaps at the edge where space-time warps unpredictably, could spawn a bubble of true vacuum that expands at light speed, rewriting the laws of physics as it goes. One moment, the cosmos exists as we know it. The next, everything, from galaxies to fundamental particles, is erased, replaced by a new reality with alien rules. The scariest part, this could happen at any instant with no warning. But the most profound revelation lies in entropy. The second law of thermodynamics dictates that disorder always increases, pushing the universe toward heat death, a state where no energy can be extracted, no stars shine, and no life survives. The edge, where expansion isolates regions of space like islands in an ever-growing ocean, accelerates this process, yet even here there's a glimmer of paradox. Some quantum gravity models hint that in the far, far future, random fluctuations could birth new universes from the void Boltzmann brains, spontaneous big bangs turning the edge from a graveyard into a cosmic nursery. So which fate awaits us? The truth might be stranger than any single theory. Observations of distant supernova, the cosmic microwave background, and even gravitational waves are painting a picture where multiple forces, dark energy, gravity, quantum effects battle for dominance across different epochs. The edge isn't just a passive bystander, it's an active participant shaping the universe's destiny through its hidden geometry, its unseen dimensions, and its quantum storms. Ultimately, the universe's fate isn't just a scientific question, it's a mirror. A cold, infinite expansion reflects a cosmos indifferent to life. A cyclical rebirth suggests resilience. A sudden vacuum decay speaks to fragility. And as we peer toward the edge, searching for answers, we're really asking, is the universe a story with an ending, or just a single verse in an endless song? The edge keeps its secrets for now, but every telescope, every experiment, every theory brings us closer to reading the final page. From the haunting void of Boötes to the eerie pull of dark flow, from the cosmic conundrum of the missing baryons to the spine-chilling possibility of phantom energy, we've journeyed through 30 of the universe's most baffling mysteries, each one a humbling reminder of how much lies beyond our grasp. Just when we think we've mapped the cosmos, it throws us a curveball, a cold spot that shouldn't exist, a horizon we can't cross, or whispers of other universes brushing against our own. The deeper we look, the more we realize the universe isn't just stranger than we imagined, it's stranger than we can imagine. Consider this, every mystery we've explored today isn't just a gap in our knowledge, it's a doorway. The Great Attractor yanking galaxies toward the unknown, the holographic principle suggesting reality might be a shadow play, even the Boltzmann brain paradox making us question the nature of existence itself. These aren't dead ends. They're invitations to rethink physics, to challenge assumptions, and to stay relentlessly curious. Because history has shown us that the biggest breakthroughs often come from chasing the very questions that seem unanswerable. Think about how far we've come. A century ago, we didn't know galaxies existed beyond the Milky Way. Now, we're debating the shape of space-time and the fate of the cosmos. Tomorrow, we might uncover truths that rewrite the textbooks yet again. Maybe we'll find the missing baryons hiding in dim cosmic threads. Maybe gravitational waves will carry voices from beyond our horizon. Or maybe, just maybe, we'll stumble upon a mystery so profound it makes today's puzzles look like child's play. So here's to the edges we can't see, the questions we can't yet frame, and the discoveries waiting just beyond the reach of our telescopes. The universe doesn't owe us answers, but it does offer us this, the thrill of the hunt, the joy of wonder, and the endless reminder that the greatest stories aren't the ones we've told, they're the ones we've yet to uncover. Stay curious, the cosmos is just getting started.